Hey guys, so today I'm going to be doing a video on force and momentum. This comes from the last playlist where it's about Newton's laws of motion. So now I'm going to be talking about Newton's laws of motion, but associating them with or relating them with momentum, okay? So it's going to be a brand new playlist with this name, force and momentum. So momentum, in case you don't remember what it is the mass of an object times its velocity. Because the mass comes in kilograms and the velocity is in meters per second, the unit for momentum is kilograms meters per second, okay? And if you look at the video, the video is later. If you look at the symbol equation, is P equals m times v. Now, momentum is a vector, so that means that it has a size and a direction. So magnitude, and then you need to have it positive or negative according to what you decided to be the positive or the negative momentum. If you forget about the signs, you can, you get your calculations wrong, and if you're doing this in an exam, you don't get the marks. Now, Isaac Newton said that a force is needed to change the velocity of an object. Now, Newton's laws of motion, they can predict the motion of all objects in all situations with the exception of three different things. Number one, if we are talking about stuff inside the atom, this is because those formulas don't work. That's more quantum physics, so you need to apply quantum physics. Number two, if you have speeds that are higher than 0.42 c, where c is the speed of light, so 0.42 the speed of light, this is because we get into the relativity field. And I think I have a video, or maybe not, about relativity. If I don't, it will be soon enough. And the last one, when I have very strong gravitational fields, and again, relativity takes place there, okay, is in action there. So in those ones, you need to use other equations. And for example, especially in relativity, Einstein's equations, they work for every single situation, so even these ones with Newton's. It's just that they simplify into the equations of Newton for speeds much lower than the speed of light and for situations where the gravity is not very strong. So you could even use Einstein's equations instead of using mass times velocity, but for everyday life, in normal, let's say, situations, that's, it's not going to, the results are basically the same, or the same. I'm going to add that link in the description. I actually do not remember, but I think it's just some exercises on momentum, in case you don't remember how to do them, okay? Now, momentum and Newton's laws of motion. So, Newton's first law of motion said that an object remains at rest or in uniform motion unless is acted on by a force, an unbalanced force. So that means that an object is going to change their movement if a force is applied to it. So, if the resultant force is zero, the momentum is constant. Therefore, the object's velocity is constant. And if a moving object has a constant momentum, gains or loses mass, the velocity changes in order to keep the momentum constant. So basically, we are just saying applying the law in terms of momentum, okay? Newton's second law of motion said that the rate of change of momentum of an object is proportional to the resultant force on it. So instead of saying force equals mass times acceleration, you can say that instead because you're relating it to momentum, sorry. So it means that the resultant force is proportional to the change of momentum per second. So I can put that in that formula, F equals dp over dt, so with the derivatives. And it's very easy to show that F equals dp over dt. What you do is the following. You know that force equals mass times acceleration. Assuming that the mass is constant, you can take it out and you simply get the dv over dt, because the dv over dt is going to be acceleration. So again, because the mass is going to be constant, it doesn't matter if I have it inside or outside. The derivative is I think that's how you call it in maths. So I can put dmv over dt equals the force. But mv is momentum, so I just show that dp over dt equals force, okay? I also can write it as F equals lambda. No, is that a lambda? Oh my god, I forgot the word. I think it's a lambda. Well, the change of delta is a delta. Oh, see? I'm not thinking straight today. Delta mv over delta t, okay? And this equation works at all times, either if you have force equals mass times acceleration, when if you have force equals mass times acceleration, it only works if the mass is constant. So I'm going to say it again because I messed it up. So the force equals mass times acceleration, but that only works if the mass is the same. But imagine that I have a situation, and you will see very soon, where my mass changes. Then I can write the formula as force equals the change of mass times velocity over the change of time, okay, or the time that it took. Now, I can use it in both situations, as I told you. So if I have, for example, that dog in there, the mass is constant, I can say that force equals the mass times the change in velocity over the change in time, so force equals mass times acceleration, because remember that change of velocity over time is acceleration. Now, imagine that I have a rocket. I have the rocket is full of fuel, but as the rocket is moving, the fuel is being consumed. Therefore, the mass changes, and is going to be changing at a constant rate. So then I could use that the force equals the velocity times the change in mass over the change in the time, or the time that it took for this to change. Where the change in mass over the change in mass and the change in time, so delta m over delta t is the change of mass per second. This is obviously assuming that my rocket keeps the velocity the same, okay? And because we're talking about rockets, why not talk about jet engines? So I have there a video that tells you every step of the jet engines, and remember, and you know that already because I told you that in a video in the past, the jet engine is a great example of the law of action-reaction, so Newton's third law of motion. So basically I just went through all the three laws of motion, but associating them to momentum. I don't know why I'm saying moment today. Momentum, okay? I also like to call the law of action-reaction karma, because it's easy for you to see, so you do it on one side, you get it back the same, okay? So, lastly, change of momentum. So we spoke about momentum in terms of Newton's laws of motion. We spoke about what it is. So why don't we talk about the change of momentum? There is this formula that I told you already in a video, I think, yeah, in the car safety, that says that impulse equals the force times the acting time. So that means that impulse, I, equals F times delta t, the time that it took me, and that's the same as the change of momentum, okay? So it's the same as the delta mv, where mv is p, the momentum, okay? This is because saying impulse or change of momentum is the same. So momentum, or the impulse or the change of momentum, equals the mass times the final velocity minus the mass times the initial velocity, okay? Because I'm only talking about changing momentum, it's going to have the same units. So it's going to be newtons, kilograms meters per second, or kilograms meter second minus 1, or then newtons times second, because it's force times acting time. I have here an example of a graph of force times the acting time. This is, for example, if I hit a football or if I hit the golf ball, which you're going to see in a video soon enough. So this is the duration of the time in milliseconds. If I look at this shape, and if I get the area under that line, I get the area of force times the time, the acting time. So the area under the graph of a force time graph is going to represent the change of momentum, or then I can say the impulse of the force, okay? I think that's all. Yeah, it is all. Impact forces, that's next when I'm going to show you the golf ball. So that's all for today. I hope it made all sense for you. If not, you already know you can come to me and speak to me directly, or just drop me a message. Up to my next video. Be happy and healthy. Take care. Bye.